Well, we are in the study of Genesis, the first book of the Torah. Well, we are studying the book of Genesis. In fact, we are in session 3, which will deal with the second day. But before we get into this a little bit, let me tell you very frankly that of the 6 days, we're going to cover a session on each of the 6 days. And as we do that, I want to let you know up front, this is probably the most difficult of the 6. And so one of the difficulties you and I have is not trying to reconcile the book of Genesis with science. Our biggest problem is the bad science that we've all been programmed with. You and I, as just members of this culture, let alone products of the school system, have been taught, I use that in quotation marks, so much mythology, so much nonsense, that part of the burden of approaching this book is to somehow set aside these presuppositions that we bring to the subject. If we really somehow could erase the blackboard, start fresh, as our very young people can, and immerse in the scripture to see what it says, point one, and then if we need to put it against a fabric of background, put it against modern, current, real science, not the nonsense that have filled our textbooks over the last many decades. So one of the only real barrier to truth is the presumption that we already have it. So one of the things I'm going to try to remember to do as we go into each one of these sessions is to remind you that whatever presuppositions you might have, be they right or wrong, just put them on the shelf for this hour and try to be open to what God may be saying. Now, having said all that, I'm going to also admit to you right up front that I'm going to take the opportunity to explore some what you might consider fringe areas that are around our topic. If for no other reason than to stretch our horizons. So as we read the text, we don't impute to the text the presuppositions that we may have been programmed with in the past, but take advantage of the incredible insights of recent years from the scientific community. And I'm going to suggest that the more you really know about what the text is saying, and the more you're sensitive to the advanced thinking in modern science, which in itself is not free of controversy, of course, the more you know both of those things, the more you'll see them congruent. And so in that spirit, let's just jump into Genesis, second day. And that's chapter 1, verses 6 through 8. And the first session we had an introduction to the Torah. For those that may not have been here, I'll highlight quickly. We talked about the authorship of Genesis. Make no mistake, I know who wrote the book of Genesis, despite all the seminary stuff, all the nonsense you hear about the masquerades under the thing they call the documentary hypothesis that was JEQ and all that nonsense. Jesus Christ told me who wrote it. Moses did. So if you believe in Jesus Christ, you can save yourself all that effort. You know who wrote the book. If you don't know Jesus Christ, you got bigger problems in the authorship, so I won't get into that of the book of Genesis. It is the book of beginnings. Every theme in the Bible starts in Genesis and gets climaxed in Revelation. In fact, every climax in the entire Bible has its beginning here in this book. We talked a lot about the nature of time. The great discovery you and I have, the great advantage that you and I have, is that we know today that time itself is a physical property. It's a property of the space. Our space is a four-dimensional continuum. Planck's constant is a four-dimensional constant. Time is a physical property. What that means is that God is outside time. Eternity is not a question of having lots of time, it's a question of being outside that environment. So we went into some of that very fundamental stuff. It will lift the veil on a lot of controversies that go right through the whole Bible. We talked about the age of the earth, and there is an abundance of evidence that the earth is young. And that shocks many people, including many scientists, because especially people from an astronomy background, an astronomical background, people with a geological background, have been programmed to take for granted millions and millions and millions and millions of years. And it's astonishing to discover. It's not by no means a totally agreed upon thing, but there's an enormous evidence that the Earth is much younger than is commonly accepted. A lot of evidence for that, and we'll touch on that throughout the whole series here and there. And I think I point out to you that there's a book called In 6 Days, where 50 of the top scientists in the world acknowledge that they believe in the six-day creation. So these are issues that are important, and we will deal with them as we go. And we talked a little bit about pi and e. I won't get into that here. And in the last session, we had what was called day one. Not the first day, day one, the first of days, an ordinal number, when the Holy Spirit was moving. And we used that opportunity to explore the possibility, maybe, that there was a gap between verses 1 and 2 of Genesis, the so-called gap theory. We talked a little bit about when were the angels created before the earth. When was Satan created before? When did Satan fall? No one knows, but apparently he fell prior to chapter 3. So that's conjecture that we talked about. But more importantly, we also focused on the nature of light itself. The first direct quote of God, let light be. And so we talked about that. That's going to also echo through the rest of these days. But we are tonight exploring the second day, Monday, if you will. And we're going to talk about the stretching of the heavens. We'll talk very little, but we'll touch upon the Big Bang models that I'm sure you've heard about. But we're going to focus on what is this thing called space. Most of us think that space is an empty vacuum. And it's astonishing to discover what they have now determined about space itself. And we'll talk a little bit about hyperdimensions. And I'll introduce you to two friends of mine. And I want you to be very, very compassionate when I introduce my two friends. Because these two friends I'm going to introduce to you have a very serious handicap. They live only on 2 dimensions. And we'll talk about that when we get there. So we're in the second day. In the next session, of course, we'll talk about life and vegetation and the origin of life. That'll be the next time. The following one will be about stars and planets. Now, that's very interesting. Do you realize the vegetation came before the sun? That's interesting. We'll talk a lot about that when we get into that. Fish and fowl on the 5th day. And, of course, animals and man, Mr. and Mrs. Man, on Friday, the 6th day. And then the 7th day, which has its own surprises. So let's just jump in. Last time we started Genesis 1, verse 1. In the beginning, God created the heaven and the earth. If you understand that verse, if you accept that verse, if you embrace that verse, you will have no problem with the rest of the Scripture. Everything else derives from that. If you can grab that one, you've got it all. If you stumble there, you've got to go back and do some homework. And the earth became without form and void. Darkness was upon the face of the deep, and the Spirit of God brooded or moved above the face of the waters. And God said, let there be light, and there was light. And God saw the light that it was good, and God divided the light from the darkness. Divided the light from the darkness. I thought darkness was the absence of light. No. There is a kind of darkness that's solid. There's a kind of darkness that's so solid that light can't escape from it. We call them black holes and so forth. So it's a little more complicated as we go here. It's astonishing to me that the more you know about particle physics, the more you know about the frontiers of science, the more comfortable this whole text reads. It's not a quaint rhetorical device for ancient people who had no background. That's the way a lot of people read this. It reads so it could do that. But it's even more astonishing, the more sophistication you have, the more comfortable these passages will be. Let's move on. And God called the light day, and the darkness he called night, and the evening and the morning were day one. And be careful about that. We'll talk about that today again. But the word evening and the word morning may have meant something different back then, the very, very early dawn of history. And those words came later to mean evening and morning. So let's be careful about that. We'll talk about it as we go. But now we are in the second day for tonight. And God said, let there be a firmament in the midst of the waters, and let it divide the waters from the waters. And God made the firmament and divided the waters which were under the firmament from the waters which were above the firmament, and it was so. And God called the firmament heaven. And the evening and the morning were the second day. This is the day that is the most difficult to address, and I think one of the problems is vocabulary. We're dealing with some different... First of all, here we have what on earth is the firmament? Strange word. And it's in the midst of the waters, and it's going to divide the waters from the waters. Does that sound like double talk? Confusing, isn't it? Well, let's go and take a look at this now. There are alternative views of what we mean by a day. I think we've talked about this before. There is a hypothesis held by many Christians that the days are a rhetorical device for ages, the ages hypothesis. And they notice that days 1, 2, 3, there was no sun. You have plants but no sun. And so that creates kind of a problem trying to make those very long. How long can a plant survive without photosynthesis, right? And then there's the other strange aspect. The seventh day has no evening and morning. Does that mean the seventh day, if these are ages, are they still going on? Now, I'm not here to either sell, but I can tell you very candidly, it's relatively easy to shred the ages hypothesis. And I'll show you the climactic argument in the end. That's why I'm not going to spend a lot of time on it, nor am I going to spend a lot of time taking it apart. I'll show you why in a minute. There is another approach to the days, the 6 days of creation, and that's what, there's a family of ideas that you could put under the idea of a framework hypothesis, that this was just a framework to communicate something in a broad sense, a rhetorical device. And, but this would create a disjunction between taking the Bible literally and taking it just as literature, to assume that this is just some kind of poetic license. Some people call the creation hymn. Well, indeed, that segment of thing reads in a very particular style. And so some people build on that and say, well, this is just a literary device. We don't have to take the days seriously. And they notice there's a parallelism between the first 3 days and the second 3 days. If you put them side by side, there's a certain kind of parallelism they point to. And but the real thing that you got to, and there's also no rain. We don't get rain until chapter 2, verse 5. And there's so forth, and the plants and all that. So there's another variation of that which argues that this whole scenario we're reading in the first 6 verses is like a panorama to an earth observer. There was no one on the earth yet. God's there, and Adam has not been created yet, but it's written as if there's someone watching all this going on. That's another view. Again, these ideas are rhetorical. They treat it as a rhetorical device to get out from under what they think they know about the history of the earth. Part of the problem is we're pretty mixed up about the history of the earth. The more we learn in modern science, the more it draws us closer to Genesis 1, by the way, and that's what I'm going to try to show you this evening. But let me tell you why I, for one, as a technical specialist all my life, I joined those, I hold the view that we're talking a literal 24-hour day. And I'll tell you why I believe that. And that's because God wrote it personally in stone. In Exodus chapter 20, verse 11, right in the middle of the Ten Commandments, he clearly instructs us to understand that he did it in 6 days. Just as I did this in 6 days and the rest of the seventh, I want you to rest on the seventh. In other words, clearly God intended us to understand it as 24 days, 24-hour days. So that gives me a problem if I'm going to try to make it something other 24-hour days, because I'm going against God. I don't think God lies. I don't think he deceives. I don't think he indulges in misleading rhetorical devices. And in fact, 8 times in the Tanakh, it says the Eternal One cannot lie. It's against his nature. And so Exodus 20, verse 11, is the end run on all this philosophical discourse about was it really 24-hour days. God said so, and it wasn't casually. He wrote it with his own finger in stone. What more do you want? So let's move on. Proverbs 8, verses 8 and 9 says, God says, all the words of my mouth are in righteousness. There's nothing froward, or twisted, I should say, or perverse in them. They are all plain to him that understandeth, and right to them that find knowledge. And by the way, that word froward means twisted. God doesn't twist, doesn't play, I got you kind of games. He's very straightforward. Boy, can we take comfort in that. And the word plain, nakoch, means straightforward, uprightness. This is straight stuff. So I don't think God built it in such a way as to mislead us. And so So back to verses 6 and 7. God said, let there be a firmament in the midst of the waters, and let it divide the waters from the waters. God made the firmament, divided the waters which were under the firmament from the waters which were above the firmament, and it was so. Now, the word firmament is one of the problems here. We've got a vocabulary. The word is rakia, and it's translated in our Bible as firmament. I'll show you why when we go into it a little more depth. But we have all through this passage the word waters. And there are many really competent Christian scientists that are Christians that take this as H2O. And it may be. But it doesn't necessarily have to be. I'll come to that. But I want you to, first of all, understand it may be waters as you and I think of them. I'm not ruling that out. The word ma'im, it's a very strange word. The word ma'im has a meaning of being water or waters. It also can mean danger, violence, or transitory things, interestingly enough. And its original word was a dual. It's always used as a singular, but it has a plural nature to it. And it's one of those strange words. In Psalm 104, we find it's all about water. God created the waters and the clouds, we find, on the earth. He controls their boundaries. He appoints springs to break out, verse 10, rain to fall at his bidding. And in its doing so, it, of course, fructifies the earth, brings forth fruit, and gladdens the heart of man. And because of all this, the word waters can also be used idiomatically to represent those things. We speak of Jesus Christ as the living water. Does that mean he's H2O? No. It means he's a source of refreshment, a source of cleansing. You're using a figure of speech that's very valid. You understand me? So the word waters can be used rhetorically. In fact, that's part of the possibility. The word ma'im could be used as a metaphor on the one hand. There's also a very commonly used figure of speech called a synecdoche. That's where you put the specific to mean the general, or the general to mean the specific. To give you an example, you might say that so-and-so sets a beautiful table. You don't mean just the place settings, you might mean her whole cuisine. Do you follow me? That's a synecdoche, where you use the specific, really pointing to the whole class of things. And that's a very common figure of speech. You say, does the Bible use figures of speech? Absolutely. You'll find synecdoches, of course. You'll find puns. You'll find metaphors. You'll find similes. You'll find allegories. Do you know how many different categories of figures of speech you find in the Bible? Over 200. And they're cataloged for you. We include it as an appendix in our book on the Bible codes. And give you an example, and the verses, an example of each one of them. There's actually 200 different figures of speech in the Scripture. But that's what they are, figures of speech, mechanisms of communication. Now, the word ma'im might be vocabulary, ancient vocabulary, to embrace what you and I would use today, if we were knowledgeable, for the term plasma. Plasma is the fourth state of matter, and that's a state of matter before molecules form. Now, let's just talk water. We started with water. Let's talk a little bit. Let's try to understand about water. Now, this is a little chart, temperatures going vertically and calories per gram on the right side. If you take water as a solid, you have ice, right? How many have experienced ice here at Idaho? Okay. But it gets to a point where if you add, 80 calories per gram, and you get water. The ice melts, becomes liquid, right? You keep adding heat to that, and you get steam. The steam is a gas. And you can heat that, the steam can carry lots of energy. Those of you that have been in mechanical engineering, the Rankine cycle. As a Naval Academy graduate, let me tell you, we learned about the Rankine cycle, because the steam is still a very big deal in the Navy, and so on. So, and you finally get to the point where you have superheated steam. But if you keep adding heat, you go beyond steam. What happens beyond steam? And that's what we call plasma. That's when the molecules themselves actually ionize. So plasma is made up of ions, that is just the nuclei of the atoms, and the free electrons. And it behaves differently than the gas does in some interesting ways. So most people know there's 3 states of matter, a solid, liquid, and a gas. No, there's 4. There's also plasma. And I want to talk a little bit about that. See, plasma would start we take water, which is really two hydrogen atoms and an oxygen atom. That's what we call H2O from chemistry, you may recall. Okay, let's see, the little blue dot here will be oxygen, the yellow dot hydrogen. And so initially, plasma, you might have just some oxygen atoms, and around them are some electrons freely floating around. That's a plasma. They haven't formed molecules yet. You cool that down a little bit, and you get the hydrogen atoms will begin to share electrons and become H2O molecules, but it's still a gas. It's still a gas because they still can intermix. You cool it down a little further, and their freedom of motion is more constrained. It gets to be what we call a liquid. And you cool it down a little further, and these molecules will form a lattice, and we call that a solid. It's called ice. We're going to talk about some incredibly unique properties of ice and water in our next session. But I wanted to give you this background in preparation because one of the things we see, of course, is water can be a plasma, it can be a liquid, it can be a plasma, it can be a gas, it can be a liquid, or it can be a solid. Ice, or of course snowflakes being an example, and the snowflake gives us a glimpse, of the crystalline structure of the atom itself. But the nature of matter: plasma, gas, liquid, solid. These are the four states of matter. What's interesting is going from plasma to solid, you are reducing the entropy. You're going from disorder to order. We're going to talk a lot about that all through this. The law of entropy is visibly operating here. If you have a solid, you have to add energy, add entropy, add heat, and it'll go from a solid to a liquid to a gas, or ultimately to plasma if you have enough energy. So, what are the properties of plasma? There's a guy by the name of David Bohm, and he's a University of London protege of Dr. Einstein. He's one of the most respected quantum physicists on the planet Earth, and one of the most eminent thinkers in other fields too. At the Lawrence Livermore Radiation Laboratory in the late 40s, early 50s, he studied plasmas, and he became fascinated with the behavior of plasmas, which are a mixture of ions and electrons, and because they acted as if they all knew each other. The plasma would behave in such a way, it's as if all these elements were interconnected. They all behaved as if they were part of some broader interconnected whole. That puzzled him. And we went to Princeton. He and Dr. Einstein were very, very troubled by the apparent conclusions coming out of quantum physics, and we'll talk about that in a little bit. But they knew there's something going on where you have trillions of these little particles acting as if they're somehow interconnected with each other. And that became the beginning of some background. Particles and plasmas behave in an interconnected way. And it was David Bohm that first postulated the possibility that quantum particles, these small particles smaller than an atom, they lack a property that you and I would call locality. They don't have a locality. If they're smaller than an atom, they seem to be in a whole nother manner of operating. And in David Bohm's day, they speculated the possibility that these particles don't have locality, and since has been proven. This means that all points in space become equal to all other points in space. That shatters our conception of what space is in the first place. And so, if we make a model of an atom, I think most of us in school have seen the idea of you have a nucleus and an electron going around it. This is just one way of representing an atom. It's obviously just a form of representation, but it's useful. You have a nucleus, you have an electron going around it. And this is not the scale, by the way. Let me show you what I mean by that. The atom is about 10 to the minus 8 centimeters. The nucleus is 10 to the minus 13th. Or putting it another way, that means the nucleus is 100,000 times smaller than the atom itself. 100,000 times smaller. In other words, whatever I make the nucleus, I would have to make the ring around it, if I'm going to make this diagram, 100,000 times longer in radius. Or putting another way, if I have a pinhead representing the nucleus, the electron would be a football field away, or actually 100 meters away. So these glib little diagrams we use to communicate are misleading because we have no capacity to imagine the scale we're talking about. The atom is mostly empty space. In fact, if you take 10 to the 5th and cube it, that's 10 to the 15th. 10 to the 15th is a big number. Big number. And if you imagine the universe being 15 billion years old, as some scientists suggest, that's about 10 to the 15th seconds. There's about roughly 10 to the 15th seconds in the history of the universe if you accept these ancient long ages. So it's a big number. So the volume, so an atom is mostly empty space. I sit here with a platform and you and I would suspect that that's solid, especially if I hit you with it. And yet, if I say it's empty, I'm over 100,000 times more accurate. In fact, 10 to the 15th. I'm billions of times more accurate than you are by saying it's empty. See, this platform is actually an electrical simulation. It just pretends to be solid. Spooky, huh? You think this is weird, it gets worse. Okay. So if we start making models, we talk about H2O, we have the oxygen atoms and two hydrogen atoms sharing electrons. That's the way they bond to make a molecule. You all have been through that. And if you take a carbon atom, you got multiple rings. You got 2 in the first ring, 8 in the rest. You have 4 atoms, you get CH4, and that leads to the whole hydrocarbons and carbohydrates and the whole area of life. We'll talk about that more next time. But what I want to look at just a little bit, let's go below the atom. We've glibly talked about nuclei and electrons. There are particles that are subatomic, smaller than an atom. Electrons, protons, neutrons, so forth. There are over 200 different kinds of particles, subatomic particles. There's a whole group of them that are subject to what they call the strong force. That's the hadrons. That includes protons, neutrons, and mesons. And there's those that are not subject to the strong force. Those are called leptons, neutrinos and quarks, and it gets stranger and stranger. In fact, you start talking about quarks, there's up and down, charm, strange, top and bottom, or truth and beauty. The physics profession, for some reason, got to the point where they found they had these measurable attributes and they needed names for them. And so they adopted deliberately whimsical names. They're up and down. In fact, the last one, these 6 quarks, defined what's called the standard model in physics, and they've come a long way. The last one, the top quark, was actually discovered in 1995. So this is very recent stuff. Some of this is very recent stuff. And there's even some, by the way, that are called red, blue, and green. They're not colors. These are pigments of their imagination, if I can coin a phrase. They're just labels for attributes that are abstract, and so they just gave them colorful names, pun intended. So. But what's interesting about these, and I'm not going to I was tempted to, but then I thought better of it, going through a catalog of all these crazy things, because the more you get into them, the more bizarre. You and I can't imagine something that has no mass having momentum. And so we can't imagine something that has half a spin. What do you mean half a spin? You get into some very bizarre stuff. But here's the main point. Every particle has its opposite antiparticle. And if a particle and the antiparticle collide, they annihilate each other and throw off a photon. So, okay, that's pretty interesting, but most of these equations are reversible. So reversibility could imply that light could have created them out of nothing. Because you take the two and collide them, you end up with nothing plus light. Can you take nothing and add light and get particles? Isn't that what happened on Sunday, before Monday? When God said, let light be? I think it's not just light in the sense of photons. It may be photons. It may be all electromagnetic frequencies were created, out of which all this comes. Kind of interesting. Could these things be reversible? Can you take light and nothing and get particles out of it? As long as they're balanced, why not, you see? And the whole universe consists of particles and antiparticles. I'll leave it for another time, but they've recorded positrons going backwards in time. It's the only place that we've actually seen it demonstrated. But the world of quantum physics is a weird world, and I'm not here to give you a whole course in quantum physics, but I do want you to have a respect for how weird this world is. Its non-causality goes out the window. It's non-deterministic. See, all of us, even with an engineering background, have been programmed with what's called deterministic mathematics. 2 plus 2 is 4, always. And I'll talk about precision here. It's, let's say, 2.0 times 2.0 plus 2.0 is 4.0. Always. It's called F equals ma, whatever. These are deterministic equations. That's the way engineers think. We have plunged ourselves into a world that would be classified as non-deterministic or stochastic. Nothing is certain. The chances are 60 to 40 that it'll be this way. The chances might be 99 to 100. It's this way. Never certain. The whole world becomes fuzzy. The whole world becomes probabilistic in a sense. See, nothing turns out to be real definitively in the field of quantum physics. You can't say anything about what things are doing when we're not looking at them. There's actually behavioral differences if they're being observed. And boy, does that lead to some bizarre things. So much so that Boltzmann committed suicide. He couldn't handle the implications of what they're discovering in the quantum world. Reality turns out to be non-local. Distant particles seem to be inseparably connected to some indivisible whole. And the scientists don't know what to do about it. Now, there was, in 1964, John Stuart Bell at CER in Geneva, he formulated a mathematical approach to demonstrating this concept of non-locality. It wasn't an equation, it was an inequality, but the point is it was a mathematical expression which would presumably lend itself to being tested. The trouble was they didn't have the technology in '64. But in 1982 they did have, almost 20 years later. And Alan Aspect and Jean Dalibard and Gerard de Roger in the Institute of Theoretical and Applied Optics in Paris conducted the landmark experiment, the so famous two-particle experiment. 2 photons from heating cesium with lasers traveled in opposite directions on a 13-meter, opposite directions on a 13-meter pipe. And 6.5 meters each in opposite directions to some special filters. The filters switched in 10 nanoseconds. That's 30 nanoseconds less than light would travel during those, in those 13 meters of travel between them. And the photons did demonstrate non-locality. The photons were in immediate connection all the time. It's hard to explain much more without getting more technical, but the point is they actually observed this peculiar property of non-locality. So it's no longer just a conjecture by some thinkers, it's a experimental result that they're still struggling to figure out what they mean. Niels Bohr, one of the famous scientists and atomic scientists, he says anyone who is not shocked by quantum theory hasn't understood it. If you understand it, it rattles you because it has implications that are shattering to our notions of reality. Richard Feynman, the very popular Caltech professor, said, he says, I think it's safe to say that no one understands quantum mechanics. In fact, it's often stated of all the theories proposed in this century, the silliest is quantum theory. Some say that the only thing that quantum theory has going for it, in fact, is that it is unquestionably correct. And that really summarizes up. It doesn't make sense on the one hand, yet we know without this we would not have lasers, we would not have microcircuits, we would not have semiconductors. Our whole culture in the modern age depends on the reality of quantum physics. And yet the philosophical implications of quantum physics are shattering as you get into it. But with that background, you see, we can start talking about, okay, what is this? That's the firmament. What is this rakia business? The Hebrew word rakia, the firmament, it means an extended surface. It implies a solid surface, a solid expanse. In the Greek translation, steroma means firmness, is what the Greek word, which is even more precise. And that's why in the Latin translations it's firmamentum. And the term implies three-dimensional solidity or firmness. This is a rakia. It's solid. It's not fuzzy. It's not like a gas. It's solid. Now, what happens in this day is that the rakia separates the mayim. What on earth is going on here? Now, if you take the waters literally like H2O, one of the possibilities here is that this is describing what leads to the so-called canopy theory around the planet Earth. And the Institute for Creation Research, Henry Morris and the gang down there in San Diego are outstanding, world-renowned scientists. And they first developed and have great information that supports this idea that the original world had a canopy of water around it, protecting it from cosmic rays, sort of a greenhouse effect to give it an accelerated warmth and so forth. And the canopy theory is very popular among some very competent scientists that are believers. But I want to also be candid with you. There are some very, very capable scientific thinkers that don't accept the idea of the canopy theory. It's got some problems with it. And I'm not here to strengthen it or shoot it down. I want you to be aware it exists, but it's not certain is the point. And it argues that there's waters above the earth. And now see, the word heaven, part of the problem is the word heaven can be used in an atmospheric sense, okay? It also can be like our atmosphere. It also can refer one step up to the sky. The word is used of the heavens, signs in the heavens, the stars, and so forth. The word also can mean heaven in the spiritual sense, the throne of God. So that's why Paul can speak of the third heaven, because the Greeks also, not the Hebrews, but the Greeks also, saw it sort of in three slices. There's a local heaven, that's the air that you breathe. Our planes fly through the heaven, so to speak. There's this heavens that you look at with a telescope, and then there's the heavens that you approach in prayer. And those are three different uses or applications of the same word. But rather than get down the canopy theory, something else, I thought it'd be useful to step back and let's try to put together in front of us here what we think we know about the fabric of space itself. You and I tend to jump to the conclusion that empty space is a vacuum. There's nothing there, it's empty. And nothing could be further from the truth. It's interesting. When we get more into the stars and stuff, we will, of course, go into Psalm 19, which I encourage you to read in your devotional time. But the first verse, the heavens declare the glory of God. I might add, footnote, in some ways that'll surprise you, but we'll deal with that when we get to day 4. The heavens declare the glory of God, and guess what? The firmament showeth his handiwork. Now, if the firmament is empty space, how does it show his handiwork? Let's watch closely. It's a lot of fun. The word firmament, again, same word, rakia, the firmament. The fabric of space. And I want to give you just a little bit of scientific history here because it's kind of fun to see how science adopts weird ideas and then dismisses them, proves they're not there, and then discovers later they really are. There is a thing called ether, not ether like you get in the medical department. It's spelled with an A, A-E-T-H-E-R. It's a term used for what scientists used to think of as empty space. The history of the ether hypotheses. And Aristotle, way back in the 4th century BC, taught that the physical world was made of 4 elements, air, earth, fire, and water. What tied it all together was the ether. And it was a subtle medium, a medium that put everything together. It later became known as a vacuum, after the Latin vacuus, which means empty. So the word ether is the formal name for what you and I would consider an absolute empty vacuum. We're together so far? See, the earth was believed to be fixed, immovable at the center of the cosmos. What a quaint idea. And I think there are scientists that are beginning to come back to that view for some strange reasons. But anyway, Galileo, how many of you have heard of Galileo? Okay, good. See, there's a guy that's known all over the world by his first name, not his last. But anyway, he challenged the notion of the Ptolemaic cosmology was that the sun went around the earth, and he challenged that with what we'll call the Copernican revolution, that actually the earth goes around the sun and so forth. But when you get to about the 16th century, René Descartes, he championed the idea that ether was a plenum, from the Greek word for full. Rather than a vacuum, he called it a plenum, which emphasized not its emptiness, but its fullness. They began to feel that there had to be something in between all these heavenly bodies. And he imagined that there was a very dense medium of very tiny particles that pervaded everything in constant motion, more solid than matter and yet invisible. Now, this was just his philosophical speculation. it quickly gets disproven. And yet today we find out it was closer to the truth than he probably realized. But anyway, so that was his concept of ether. And there was the secretary of Galileo was a guy by the name of Torricelli. And after Galileo died, he did his own experiments and things, and he inverted a long glass tube filled with mercury into a dish. He invented what you and I know as a barometer. And that barometer fell 30 inches, and they felt certain, among other things, that there was an absolute vacuum above the mercury. So that was obviously an empty vacuum. Pascal comes along, and he's an incredible human being. We're going to talk more about him. By the way, what's really astonishing is to understand how many of these great thinkers were believers. It's astonishing to look back in the history of science and realize that the great men, Isaac Newton, whatever, were believers. Isaac Newton wrote over 1 million words of commentary on Revelation and Daniel, and so on. I have a copy of it. But Pascal's another one of these guys. But he took Torricelli's work further and soon was convinced that the vacuum of space was really empty after all. And see, light can penetrate a pure vacuum without the necessity of a medium pervading space if light is particles. If light's are particles, like a row of bullets, you can visualize that going through empty space. And so the idea of space being empty didn't bother you, as light is a set of particles. But other experiments began to show, as I showed you last time with the twin slit experiments, they soon began to show that light has a behavior like waves. And that creates a problem, because how can waves go through? Waves need a medium to go through. There's no medium, how can waves go through? And at the time they could only envision compression of waves, like sound waves. Light turns out to be a transverse wave. But in any case, in parallel with all these controversies, there's a Danish astronomer by the name of Olaf Romer who starts to measure the speed of light, and he, of course, discovers that it's not infinite, it's a very finite speed. And now, even when you get to the days of Isaac Newton, they believed that ether was some kind of fluid. It was more fluid than solid, but it was a medium that could support waves. That's how they visualized light going through it. And then comes James Clerk Maxwell comes along, and this guy changes the world's thinking about a lot of things. He developed a set of equations that described how light waves could travel through an ether. Light waves are composed with oscillating electric and magnetic vectors in XY plane while moving in the Z direction. They're transverse waves, in effect. For a wave to exist at all in the medium, the medium must possess elasticity, which is like a spring-like property, or it also has to have inertia. So the empty space needs inertia, really. The velocity of a wave in any medium is equal to the square root of the stiffness divided by the density of the medium, in fact. So he found that ether possessed an electric field scaling parameter, which is called by the engineers a dielectric permittivity. It also has a magnetic field scaling parameter called permeability. These are measurable electrical properties of empty space. And in fact, the ratio of these two, the square root of the ratio of these is the square root of the reciprocal of the product of these is the speed of light. They're all linked together intimately. Light slows down in glass and gases and in water because the media other than a vacuum has differing permeability and permittivity. This turns out to actually mathematically explain how light can travel in different speeds in different media, which is hard to visualize if you look at it strictly as particles. He also discovered that empty space behaves like a transmission line. Any of you that are radio hams have tried to tune an antenna know that the characteristic impedance of space is 377 ohms. It has measurable characteristics. So ether now is once again viewed as a very real medium after Maxwell. It could be stretched, it could be compressed. It had resilience, compliance, and inertia. And yet no known physical substance had a stiffness to mass density ratio anywhere near the 9 to the 10 to the 16th, which was required of ether as a medium. So it's got characteristics they can measure, they can't grasp how it ever got there. So it possesses elasticity but negligible inertia. So anyway, we finally get, as a good Naval Academy guy, I have to talk about Michelson, because in 1873 he did this at the Naval Academy. Michelson and Morley did an experiment. They wanted to measure this ether. They thought, gee, if the Earth is moving through this ether, we ought to be able to measure it. So they used an interferometer, in an attempt to detect the relative motion of the earth through the ether. And no motion of the earth relative to the ether could be detected. So then this is regarded to prove that ether apparently did not exist. Now, the negative result of the Michelson-Morley experiment baffled the scientists until 1905, when Albert Einstein's theory of relativity emerged, which gave them a way to explain this all away. And the velocity of light was the same value in all reference planes, whatever the velocity might be relative to those other planes. So physics then took off in the direction of general relativity, special relativity, as we all have heard, and also quantum mechanics. It's as if the physics community has abandoned this whole issue of ether, because this proved it didn't exist. See, the whole idea of an actual ether was discarded after Michelson-Morley. What's interesting, this non-existence of ether raises other problems, but the Michelson-Morley experiment is not the end of the story. Most people think it's the end of the story. It's not. There's more coming. There's a thing called the zero-point energy. And if the temperature of a container is lowered to absolute zero, there still remains a residual amount of thermal energy that cannot be removed. That's called the zero-point energy. What's astonishing is that zero-point energy in empty space is the most astonishing level of energy you can imagine. 100 million suns integrated over 100 million years. That's the energy in 1 cubic centimeter of empty space. The vacuum that we call a vacuum is now understood by scientists to be a vast reservoir of seething energy out of which particles are being created and annihilated. It's like being at the base of a waterfall of this intense energy. That raises a question. You may have wondered about this when you're in school. Why doesn't the electron of an atom, which is radiating energy as it spins around the nucleus, why doesn't it lose energy and eventually spiral and crash into the nucleus? The electron's a negative, the nucleus is positive, you'd think they'd be attracted. Why doesn't it collapse? It takes energy to maintain an atom. Where is that energy coming from? You think it would spiral into the nucleus, and then it turns out it picks up the energy from the background, zero-point energy, and therefore it's sustained by it. Now that's interesting. That seems to be what the Bible suggests in Colossians chapter 1, verse 16 and 17. Speaking of Jesus Christ, for by him were all things created that are in heaven, that are in earth, visible and invisible, whether they be thrones, dominions, principalities, or powers. All things were created by him and for him. He is before all things, and by him all things consist. The word consist in the Greek is synesteo, sustains or holds it together. What's holding this universe together is the continuing sustaining role of the Creator in the first place. The guy that made the place is still holding it together. He was crucified on a cross of wood, yet he made the hill on which it stood. And he's holding that hill together. It wasn't the nails that held him to the cross. At any time he could have said, enough already, I'm out of here. What held him to that cross is his love for you and me. In Hebrews chapter 1, verse 1, the epistle to the Hebrews reads, God who in sundry times and divers manners spake in times past, spake in time past unto the fathers by the prophets, hath in these last days spoken unto us by his Son, whom he hath appointed heir of all things, by whom he made the worlds, who being the brightness of his glory and the express image of his person, and upholding all things by the word, upholding all things by the word of his power, when he had by himself purged our sins, sat down at the right hand of majesty on high. That's the phrase I wanted you to just notice here in the opening of the book of Hebrews. Upholding all things by the word of his power. Wow. Gives the word of God a whole other dimension in our thinking, doesn't it? Let's talk about stretching the heavens. We talked about fabric of space here. Is this more than a metaphor? In Job 9:8, it speaks of God who alone stretches out the heavens. Is that a figure of speech? Stretching, in Psalm 104, stretching out heaven like a tent curtain. In Isaiah 40:22, who stretches out the heavens like a curtain and spreads them out like a tent to dwell in. Really? In Jeremiah 10:12, he has stretched out the heavens. The Lord who stretches out the heavens, in Zechariah 12:1. Are these just figures of speech? If they are, they're an astonishingly consistent use of phrase here. In fact, there are 17 others. I won't take you through them all. You get the flavor of them. They're all very similar. Speaking of stretching out the heavens. See, we have this mentality that space is empty. We learn from our scientists that it's not only it's got measurable properties that are astonishing. Space is not an empty vacuum. It can be torn, Isaiah 64, verse 1 tells us. You can tear space, apparently. It can be worn out like a garment in Psalm 102, verse 26. That's actually one of the laws of thermodynamics. That space can be shaken. How do you shake empty space? Hebrews 12, Haggai 2, Isaiah 13 all speak of the heavens being shaken. It can be burnt up, Peter warns in his second letter, 3:12. In Revelation, it says that it'll be split apart like a scroll. Well, now that tells us a great deal, if we think about it carefully. It can be rolled up like a mantle or a scroll in Hebrews 1 and Isaiah 34. How can heaven, or rakia, the firmament, be rolled up? Well, that tells us a great deal. See, first of all, let's talk what we know about space. The zero-point energy is about 10 to the 95th ergs per cubic centimeter. That's an astonishing amount of energy. It has permittivity that can be measured. It has permeability that can be measured. It has intrinsic impedance that can be measured, and so forth. The velocity of light, some scientists believe, was 10 to the 10th times as fast then at creation as it is today, and that's the speed of the gravity waves today. They still have that high speed, apparently. That's apparently, there's a whole other frontier. I'm sparing you all that right now. But this can all be rolled up. See, in order to be rolled up, that must mean there's some dimension in which it can be thin. You can't roll it up unless it's thin in some sense, right? So we suddenly know there's an additional dimension. Whatever dimensions it has an additional one in order to roll it up. Space can be bent. It says that then there's a direction in which it can be bent toward. You see, a two-dimensional thing you can roll up because you've got 3 dimensions to play with. You've got an extra dimension. How do you roll up 3-dimensional space? You need 4 dimensions to do that. See? So there are additional spatial dimensions. That's what the scripture tells us. So this leads us now to another discussion that I want to give you a little background on. That's called hyperdimensionality. And to do this, I'm going to introduce you to 2 friends of mine. But I want you to be compassionate because these 2 people have a very serious disability. They only live in 2 dimensions. Mr. and Mrs. Flatt. And see, most of us have been taught in Euclidean geometry. That's a geometry of less than 3 dimensions. In 1854, on June 10th, George Riemann's metric tensors changed the mathematical world. He invented the tools with which we can understand dimensions more than 3. It took over 50 years for this mathematics to be applied. Einstein used it to develop his theory of relativity. And that wasn't until 1915, his 4-dimensional space-time. But then in 1953, Closing-Klein went beyond that with light and supergravity. In 1963, Yang and Mills developed the Yang-Mills field for electromagnetic. So the scientists began to realize that these higher dimensions simplify the mathematics of the universe. In 1984 and following, the latest was the superstrings, 1-dimensional strings vibrating in 10 dimensions. And there's variations of this today. But the point is, what's interesting about this is that Nachmanides, a Jewish scholar in the 12th century, over 800 years ago, concluded from Genesis chapter 1 that the universe has 10 dimensions, only 4 are knowable, 6 of them are not knowable. That's in his commentary on Genesis, published in 1263. Why do I bring this out? Because we've spent millions of dollars on atomic accelerators in the 20th century to discover, guess what? The current thing is that it's 10 dimensions. 4 are directly measurable, length, width, height, and time. We all know about that one. 6 of them are diminished so small, they're smaller than the wavelength of light, they're curl less than 10 to the minus 33 centimeters, and therefore they're only inferable by indirect means. But we spent millions of dollars to learn what Nachmanides did by doing his homework in Genesis 1. So we're suddenly talking about what's called hyperspaces, spaces of more than 3 dimensions. There's only two kinds of people that can deal with spaces of two dimensions. And that's mathematicians with special training and small children. Okay? But if I was going to try to explain to you higher dimensions, it would take a lot of time and technology and a lot of our time. That's hard to do because we haven't had any experience with that, you and I. But there is something we can gain some insights by going the other way. Let's imagine a universe of less than 3, a two-dimensional universe. And I have two people who live in such one, Mr. and Mrs. Flat. And I put them on the screen here, rather than put them on the platform so you can see me. And these two people live in a universe of only 2 dimensions. We've done things with two-dimensional universes. We call it plane geometry or plane trigonometry in school, universes of 2 dimensions. And it turns out this has some interesting aspects. When Mr. Flat looks at Mrs. Flat, what does he see? He can only see a line right on. He might be able to infer a lot about that line as it turns around. See, when I look at you, imagine only one eye. If I look at you, I see a two-dimensional representation of you. We call it a photograph. By moving around, I can integrate and get the three-dimensional effect, but I'm really dealing in an integration of two-dimensional images. You see what I'm getting at? He's got the same defect. There's something else, by the way, though. If I come along as a three-dimensional person, if I have a dimension, one more dimension than he has, I can put my finger 1/1,000,000th of an inch away from him, and another finger 1/1,000,000th of an inch away from her. I can be more intimate with each of them, independent of where they might be in their universe. You see what an extra dimension gives me? I suddenly have a whole different capability. And so my proximity to either one of them is absolutely independent of distance between them. So this is starting to give us some insights. We're 3 dimensions. God has more than 3. We can begin to understand how we can be intimate with every one of us around the whole planet Earth. If I stick my finger through their world, I'm a 3-dimensional being, I put my finger through the world, what do they see? A line, but they could integrate and realize it's a circle, right? They only perceive me as I penetrate their particular space, right? So I can put my finger near Mr. Flat, and he said, you can go to Mrs. Flat and say, guess what? I've seen God. He's like a circle. She said, that's funny. I saw him too, and there were 3 circles. So he goes to the church of the 1 circle, and she goes to the church of the 3 circles. If a sphere comes tumbling through their world, there's nothing. There's a point that grows to a circle and then shrinks. A sphere has gone through, you see. For them to figure out what shape it was, they'd have to integrate that from time 0 to time whatever, you see. So one of the questions we have to ourselves, well, how would you try to communicate a 3-dimensional object to Mr. and Mrs. Flat? They don't know anything about 3 dimensions. Let's assume we've established communication. How would we try to communicate to them what a 3-dimensional thing looks like? How would we go about it? It'd be difficult, more difficult than it seems at first. One of the things you could do is you could do it by a projection. You could take a 3-dimensional object, like say a cube, and you could maybe create a 2-dimensional representation of it. And architects do that all the time with plans and so forth. We could adopt some technique like that to try to communicate, but it quickly becomes obvious that it's not too useful. See, the same problem, suppose I was going to try to communicate to you what a 4-dimensional cube looks like. How would I go about that? You have no experience with 4 dimensions. How would you? Here's a 3-dimensional projection of a 4-dimensional cube, hypercube. There's one on the internet you can play with it. You can turn it and stuff. And by the way, the more you do that, the more you realize you have no idea what it looks like. There's another way that you can communicate a 3-dimensional object to a 2-dimensional person. That's by unraveling it. This isn't very useful, see. So what you could do, let's assume you had a 3-dimensional object like a box. You can unfold it, lay it flat, and now you see how you could have a 2-dimensional representation of a 3-dimensional box. That's called unraveling it, right? You with me so far? It turns out it's possible to take a 4-dimensional cube and unravel it, and that's called a tesseract. A 4-dimensional cube unraveled in 3 dimensions, a Hinton cube or tesseract are different names for it. This is one representation of a 4-dimensional cube. unraveled in 3 dimensions. There's only one place I've ever actually seen it used, and it'll surprise you where it is used. And that's Salvador Dali's famous painting, Corpus Christi, the crucifixion of Christ. And it astonished me to realize that Salvador Dali, among other things, was a very, very informed mathematician. He understood what a Hinton cube was, as an unraveled 4-dimensional cube, and he uses it to give an additional dimension, pun intended, to his famous painting. I think that's kind of fun, kind of interesting. Now let me show you what Paul says in Ephesians chapter 3. Ephesians chapter 3 at verse 17, Paul says that Christ may dwell in your hearts by faith, that ye being rooted and grounded in love may be able to comprehend with all saints what is the breadth and length and depth and height. What? And to know the love of Christ which passes knowledge, that ye might be filled with the fullness of God. What? Breadth, length, depth, and height? Did Paul know there were 4 dimensions? I doubt it. Was that just in his enthusiasm the Holy Spirit guided him? Very likely. Is it possible that he said things that went beyond his own knowledge? It wouldn't be the first time that in the Bible you find a prophet writing something that was far beyond, the significance of which was far beyond anything he might have imagined. I think that's kind of fun. I think that's kind of fun. The word length there, by the way, is a term that is used of time. So there's another dimension of things that I want to talk about as we're sort of I'm trying to really just strip away the cobwebs and strip away the prejudices we bring to this topic. The boundaries of reality. You know, there are 2 concepts in mathematics that we cannot find in the physical universe. There are 2 concepts that are all through mathematics. We use it all the time, but you can't find a physical example. One is randomness. The whole field of statistics advanced statistics deals with stochastic variables, random variables that have a probabilistic distribution of some kind. It turns out there's a whole world of mathematics called stochastic processes in contrast to deterministic. Most engineers are trained in deterministic equations and so forth. But those that are in the behavioral sciences, those that are that are trained in the tools of stochastic processes, a whole different world. We deal with random variables. But the interesting thing is, you cannot find a random number. It's a function required on modern computers. You have a function to give you a random number. And anybody that's done some homework on that knows they're not really random numbers. They're what they call pseudo-random numbers. They work hard to make them almost random. You do a whole bunch of them. You do tests on them to see if they're truly random. You discover that unless they've done a good job, they don't pass the tests because they're generated. The very fact that they're generated implies they're no longer random. There may be an algorithm to make it equally likely within some range of any one number being used, and you start getting into the details of that. There's a whole art form here, but the point to recognize is they have no way of truly creating a random number. And in fact, when we first, at Western Digital, when we created the data encryption chip for the National Bureau of Standards encryption thing, one of the applications of that chip was to be used in random number generators, because it gave a whole other level of randomness, if you will. But anyway, there is a field of mathematics that's just emerged called chaos theory. It's the study of the non-randomness of the universe. And what amuses me about this, now it's a very early technology, and there are papers and people that specialize in it, so-called chaos theory. But what's fascinating about it is they can't find randomness, which, by the way, pulls the rug out from under the evolutionists. Well, it all happened by chance. Really? There is no such thing as chance. Not in the provable sense. And by the way, why? We know this from the Scripture. Proverbs 16:33, the lot is cast in the lap, but the whole disposing thereof is of the Lord. The lot is in the lap of the Lord. Einstein said that. Did you know that? He said, God does not play dice. Very famous quote of Dr. Einstein. Do you know why? If he did, he'd win. There are 2 imputed concepts that are elusive or physical. One is randomness. There is no such thing. We can't find it, let's put it that way. And the other is infinity. We've all used that term. Conceptually, we know what it may mean. Can you find anything that's infinite? Only in the abstractions of mathematics, not in the physical world. Let's take the macrocosm, the universe in its broadest sense. Get the most powerful telescopes. And the great discovery of the 20th century science is that the universe is not infinite, it's finite. That's what the Big Bang is all about, among other things. The universe is finite. It had a beginning and it'll have an end. That's disturbing from a philosophical point of view, from a scientific point of view. It had a beginning. That's what the Big Bang tries to explain. And it'll have an end, because at the end of entropy, the end of thermodynamics, is that eventually there'll be a heat death. Billions of years, maybe, whatever. So we know that in the macrocosmic sense, there is no infinity. There is a point you can get to where you can't go beyond. It's not infinite. You can't go forever. But the really bizarre discovery is the microcosm. Let's look through a microscope, and let's look through a microscope that's so powerful it goes even smaller than light. We discover that everything is digital. Everything is made up of quanta. Let me give you a simple example. Let's assume I have a line here in front of me, say a couple of feet long. You would imagine I could cut that in half, right, and take what's left. I could take what's left and cut that in half, and take what's left. And whatever I've got, you've always figured I could always cut it in half and take what's left. In our imaginations, at least, we could imagine that I could do that forever. And it's a shock to discover that when I get down to 10 to the minus 33 centimeters, if I cut it in half, it ceases to have locality. There's a point, see, because everything, length, mass, energy, are all made up of quanta. It's like a piano. The difference is like a violin string or a piano keyboard. On a violin, you can make any sound depending on where you put your finger. That's why you have to have a good ear to make it from being discordant, right? On a piano, I have keys. I can't get a half a key. You follow me? It's digital. See, piano is actually a digital device. You with me? So that's what they discovered. The universe is digital, and that's bizarre. And the Planck length is 10 to the minus 33 centimeters. There's a period of time, 10 to the minus 43 seconds. If you're reading about Big Bang theories and stuff, you always talk about 10 to the minus 43. Why do they talk that? Because that's the shortest piece of time that's possible to have. There is no shorter piece of time than that. I might call it the twinkling of an eye. That's not a blink. Twinkling is another thing. It's the time it takes light to travel the thickness of your retina. So the bizarre conclusion you quickly come to is that you and I are in an imaginary environment, a simulated environment. It had a beginning, it has an end, it has a limit in its size, and as we look closely at the details, we discover it's got a grain. It's grainy. It's not made up of smooth lines, it's made up of digits, pixels, so to speak. And so you and I are in a digital simulation. That's what the Bible has been saying all along. It speaks of the physical universe as a subset of a larger reality. We call it the spiritual universe. But when you use that term, people think it's sort of fuzzy and imaginary like a ghost or something. No, it's the other way around. The real universe is what we think of as physical. The universe that we experience ourselves is a simulated small subset. Now, at the risk of getting a lot of criticism from people, I'm going to suggest that if you're in the mood for entertainment, you rent a movie called The 13th Floor. It's just a piece of entertainment, but it will shatter you in terms of its storyline. Because the whole plot line talks about these scientists that have created a virtual world. They chose LA in 1937, that they do it very cleverly. But there's a murder mystery, and the secret to the murder mystery is in that simulated world. But there is a number of plot twists and stuff that are not only fun entertainment, but if you follow that through, it will totally alter your concept of reality. And I'm not talking about Matrix, that sort of science fiction. This is a different kind of thing. But I encourage you, if you're into that sort of thing, and you might enjoy it. Our reality, that we call reality, turns out to be only virtual. It's simulated. In fact, as people try to build a model of what we think we know, David Bohm, the guy I mentioned before, he has a concept where he speaks of the explicate order. That's the tangible, everyday, physical reality you and I know. He calls it the unfolded order. And there's a larger implicate order, which is more primary, deeper, underlying the real reality. And then you say, well, this is some kind of fringe thinker. No, this is one of Einstein's proteges, and he has sympathetic report from some interesting people, like Roger Penrose of Oxford. He's the creator of the modern theory of black holes. He's supported by Bernard Espagnet, or however you pronounce it, somebody French can pronounce it properly, at the University of Paris. He's one of the leading authorities on the foundation of quantum theory itself. And Brian Josephson of the University of Cambridge, he was the winner of the '73 Nobel Prize, and if you know anything about semiconductors, the Josephson junction is one of his inventions. These guys are leading-edge, world-class thinkers, and they think Bohm is on track here. Kind of interesting. But that's what the Bible's been saying all along. I'll call it the boundaries of understanding. 2 Corinthians 4:18, while we look not at the things which are seen, but at the things which are not seen. For the things which are seen are temporal, but the things which are not seen are what? Eternal, beyond the dimensionality of time. So we have to talk about the Big Bang models. You've all heard about the Big Bang. You understand the Big Bang theory. First there was nothing, and then it exploded. And if you think that makes sense, I got some property I'd like to show you. See, the strange developments of the 20th century science is that the universe is finite and can be measured. Secondly, that the universe appears to have been expanding, although that's becoming suspect for some reasons. And that apparently the universe originated at a singularity, as they call it, in four-dimensional space. Four-dimensional space compressed to zero size. That's the concept, singularity. When you say Big Bang, there's not a Big Bang model, there's a whole handful of them. The steady state model was the first one, but Einstein admitted it was the biggest mistake in his career. He went to his death with that in writing. Then there came the hesitation model. It was refuted in the 60s, so I'm not going to take you through it. It would waste your time. There's an oscillation model that it expanded and contracted and so forth, except the entropy laws shred that, and it also doesn't have enough mass and so forth. They work out these ideas and then subject them to scrutiny, and they all fall apart. The current version of it is what's called the inflation model. It's got some problems. It requires anti-gravity forces that have never been observed, among other things. And anyway, it's what they are. Let me stand back now. We've talked about a lot of stuff. Let's stand back and talk about how do you analyze risk. And it turns out that in actuality, something can be true or false. That's pretty straightforward, right? And you might conduct some kind of experiment or investigation from which you come to a conclusion. Your conclusion can be that it's either true or false. So what a mathematician in game theory calls the states of nature are true or false, and your data is saying it's either true or false. The question is, obviously, if things are true and your investigation says they're true, that's great. You found out truth then, right? If, on the other hand, things are false and you investigate and find out they're false, you're okay. So those two conditions are great because you found out what is actually the case. Here's the problem. What happens if something is true and you conclude it's false? That's called rejecting a true hypothesis. That's what Pearson in statistics would call, it's a classic label, is a type 1 error, rejecting a true hypothesis. The flip side is also possible. You might accept a false hypothesis, something that's not true that you think is true. That's a type 1 or a type 2 error. Type 1 is rejecting a true hypothesis. Type 2 error is accepting a false hypothesis. You get the picture so far? Now, in most cases in life, you can evaluate the risks associated with either error. Obviously, there's no risk if you're correct. What's your risk if you're wrong? You with me? One way you can be wrong is you can reject a true hypothesis. That could be disaster on the topics we're talking about. On the other hand, you might accept a false hypothesis, you've lost nothing. You see the difference? One's a huge loss, one is in fact, the guy that first proposed this is Pascal. Blaise Pascal. It's known as Pascal's wager. The key phrase of it is, he says, let us assess two cases. If you win everything. If you lose nothing. Okay? That's what he's going to suggest here. But you must wager. There's no choice. You are already committed. Which one will you choose? He says. Let's see. Since a choice must be made, and let us see which offers you the least interest. You have two things to lose, true and the good, and two things to stake, your reason and your will, your knowledge and your happiness, And your nature has two things to avoid: error and wretchedness. So that's the domain we're dealing with. Since you must necessarily choose, your reason is no more affronted by choosing one rather than the other. That point is cleared up. But your happiness, let us weigh up the gain and the loss involved in calling heads that God exists. Let us assess the cases. If you win everything. If you lose nothing. Do not hesitate then. Wager that he does exist. That was Pascal's famous wager. And so one of the questions you might ask, why are we going through all this now? Well, because a lot of people are interested in the book of Genesis. That's great. But there's some other reasons that I want to just put in front of us here. You need to understand that the coming months and coming years are propelling us to the climax of all history. And I'm going to put something up on the screen that I want you to challenge. If you accept what I put on the screen, you flunk the course. We believe that we are being plunged into a period of time about which the Bible says more than any other period of time in human history, including the time that Jesus walked the shores of Galilee or climbed the mountains of Judea. That's a preposterous statement, but I challenge you to challenge that statement. You've got to do two things. You've got to find out what the Bible really says about these days, and you've got to find out what's really going on in the world. And we're anxious to help you. We have a website that attempts to do that, khouse.org, and there's other materials, but I encourage you to use whatever resources you have to find out what's really going on and find out what the Bible, not what Chuck Missler said, what the Bible says about these things. Now, I'll just finish. We talked about Erev and Boker. I want to bring this out again. Erev means obscuration or mixture, increasing entropy. When the encroaching darkness began to deny the ability to discern forms, shapes, and identities, therefore it was also used as a term for twilight, the time of approaching darkness, and sunset. It also marks the duration of impurity when the ceremonially unclean person became clean again, Leviticus 15. That's the word Erev. Therefore, it's the beginning of the Hebrew day. Boker is the other word. It means becoming discernible, distinguishable, visible, the perception of order, the relief of obscurity, decreasing entropy, we would put it. It's the attendant ability to begin to discern forms and shapes and distinct identities, breaking forth of light and revealing things. Therefore, of course, it's the dawn or the morning. Now, if you build an entropy model of the universe, of course, entropy is, maximum entropy is at the bottom. Think of the bottom as chaos and the top as order. And Erev is obscurity or disorder. It later became meaning evening, but let's use it as disorder. Boker means orderly or discernible. So Erev and Boker makes day one. Okay? Then again, we have Erev and Boker for day two. Now this, incidentally, is the only day, this Monday, is the only day in which God doesn't pronounce it good. All the other days, he did this and that and saw that it was good. He doesn't do that on Monday. Confirmed your worst suspicions about Mondays, didn't it? But relax, he gives two blessings on Tuesday, and I'll explain why next time. But on Tuesday we have Erev and Boker. It gives us life, vegetation. But I have a question for you. Photosynthesis before sun on the fourth day? What's going on here? This is also the day of double blessing, and I'll explain that next time. And we have day 4, from Erev to Boker, where we create the planets and the sun and so forth. When was the earth created? What day was the earth created? Remember verse 1? In the beginning, God created the heaven and what? The earth. It's been there all along. Uh-oh. That's weird. That's got some interesting implications we'll talk about next time. Then we get to the day 5, Erev and Boker. We have the fish and the fowl and all that. And then, of course, day 6, we have Mr. and Mrs. Man, the animals, and Mr. and Mrs. Man. And then, of course, we have day 7, which has no Erev and Boker. Why? Because there's no creation. There's no reduction of entropy on the 7th day. It's finished. And so I suggest that as a possibility. So we've been on Monday, the 2nd day. We talked about Big Bang models, fabric of space, hyperdimensions, quantum physics. The toughest day that are in the whole series. So relax if this has been a little bit of heavy for you. Next time, we'll talk about the origin of life, thermodynamics and entropy, a little more simply, and some molecular chemistry. And then, of course, we'll get into the nebula hypothesis and a lot of other strange stuff you probably haven't taught. And the fifth day, of course, the fallacy of evolution. I think we'll put the final nails in that coffin. And DNA, of course, is the incredible discovery of our recent days. And then a lot of surprises on day 7, and that will be the front end, if you will, of our study of Genesis. We're not going to go this deeply all the way through, relax. But we felt this is so foundational that we'd spend the time. But for next time, though, I want you to answer the question in your own mind. Is there life on other planets? We'll talk about that next time. Could life have started on its own? We're going to see life for the first time in the next session. And on which day was the earth created, and which day was the sun created? Think it through. How could you have photosynthesis without the sun? So with that, let's stand for a closing word of prayer. One thing I think we will all carry away from these excursions is obviously not the technology, it's just a survey kind of thing. But the one thing I'm hoping it will get across is a new awe of our Creator. We obviously see that when we explore the heavens. We also see that when we look through a microscope. But we'll see that in more ways than we previously could have imagined as we go through these 6 days. The Creator of the universe and His handiwork, who not only did all these things, He became a man and dwelt among us so that we could behold His glory. The glory of the only begotten of the Father, full of grace and truth. Astonishing. He was crucified on a cross of wood, and yet He made the hill on which it stood. Let's bow our hearts.